In the previous lecture, we discussed the notion of a DFA, deterministic finite automata, that can recognize a language or string using a machine with a finite number of states. In this lecture, we will discuss a more general version of a FSA called non-deterministic finite state automata. Unlike FSAs, the machine can transition into multiple states from a given state, hence the term non-deterministic. More importantly, NFSA, or non-deterministic finite automatas, have applications in regular expressions. Regular expressions are widely used in Linux utilities like grep. So let's get started. There's a duality between regular expressions and DFAs. In other words, regular expression, we say, is a concise way to describe a set of strings, and a DFA is a machine to recognize a given string in a given set. Regular expressions and DFAs are equivalent. That is, given a DFA, it describes a regular expression, and given a regular expression, it describes a DFA. Later we will learn how to build DFAs by first building an NFA to recognize regular expressions. Kleene's theorem states that for any DFA, there exists a regular expression that describes the same set of strings. For any regular expressions, on the other hand, there exists a DFA that recognizes the same set of strings. Stephen Kleene, who was at Princeton, is the first to prove this equivalence between regular expressions and DFAs. Although it might be exponentially harder to build a DFA for any regular expression, it proves that theoretically it's possible that we can do so. So let's take a look at an example. On the left is a regular expression that describes some patterns. That is, a pattern either 0 or more zeros, or 0 or more zeros followed by 1 0, 1 0, 1 0, with zeros can be repeating more than once. But what we realize is that if repeated, the machine can recognize strings with ones the multiple of 3. In other words, any string that's generated from this one must have a multiple of 3 ones, multiple of 3s. Now you can have any number of zeros here. So if you look at the DFA that can describe this machine, you enter the DFA from the state 0. As long as you get zeros, you can stay there and you can leave. It's an accepting state. If you get a 1, you go to a 1, and you can stay here as long as you want. When you get another one, you go to 2, stay here with a 0. When you get another one, you go back to 0. And you can keep going, getting more strings, or you can just leave. But in any case, if this machine only accepts a lot of zeros, all zeros, or strings with multiple of 3, or ones which is a multiple of 3. Limitations of DFAs. Building a DFA to recognize something like this can be really hard. It can be really, really difficult. So let's take a look at that. Okay, now let's take a look at the definition of an NFA. A non-deterministic finite automaton, or a machine, is defined by a set of states and set of input alphabet and a transition function and the S0, which is the starting state, and a set of final states. Now, the difference between a DFA and an NFA is in here. For a DFA, given a state and an input symbol, it has a unique state that it'll go to. Now here, given a state and an input symbol, it could go to more than one state. For instance, we can have a function which goes from state Q0, and when given the symbol A, it could go to another, not just to a single state, but it could go to a set of states like Q0 and Q1. So notice this is a subset of the power set of S. All right, so let's go to and do the workshop here. So we want to build an NFA for the pattern A star B A. First of all, let's try to understand what's accepted by this regular expression. You can either accept A by itself, or you can accept B because this says 0 or more A's. So you can accept A or B, or AB, or AAB, or any number of A's followed by a B. So now let's see how we can build an NFA for this expression, regular expression. So we're going to start with two states, Q0 and Q1. So Q0 and Q1, and then we will define what happens if you get an A. So it's like two machines. If you get an A, I could stay here and wait for a B, for this one here, or I could just go to Q1 and make the Q1 the accept state. Now, if you stay here, so you can think of this as two machines. One is the machine just recognizes A, another machine that recognizes B, or get any number of A's and recognizes a B. And Q1 is the accept state here. So you can see that this regular expression is represented by this non-deterministic finite automata. It is called non-deterministic because you can see that on Q0, if you get an A, either you can stay in Q0 or you can go to Q1. So you get a combination of states here. And if you get a B in Q0, you go to Q1. So this is the table that represents the transition table that represents the NFA. It's called NFA because we don't know if you're in Q0, if you get an A, should we go to Q0 or Q1? In this case, it can go to either one. So let's suppose that we want to show that the NFA representing A star BA can be converted to a DFA. So let's go through the process of doing that. Now here's the table we got for the NFA. So what we're going to do is we're going to assume that this is a new state, Q0 and Q1. We call that Q2. So in the Q2 state, we complete the table. If you're in Q2, what would you do if you get an A? What you're going to do when you're in Q2 is the same as what you're going to do in Q0 and Q1, because Q2 is the combination of Q0 and Q1. That means it's the union of whatever actions you take here. But here, Q0, Q1 is called Q2, so I'm going to just write Q2. Same thing here. The action you're going to take when you're in B is a combination of the actions you take in Q0 and Q1, because Q2 is the combination of Q0 and Q1. So we take the union of these states, which gives you Q1. So here's the new picture. Now we introduce a new state called Q2, which also becomes an accepting state, because Q1 is an accepting state and Q1 is part of Q2. Therefore, Q2 also becomes an accepting state. Now, all we have to do is to convert this table and show the actual DFA. So now it is not non-deterministic anymore, because if you're in Q0, now it goes to Q2, which we call Q0, Q1. Q2 is the new state we introduce. From Q2, if you get an A, you stay in Q2. If you get a B, you go to Q1. So the question is, does this accept the same strings as the NFA that's here? Which is true, because this NFA accepts A, B, AAB, AAB, and so on. So this DFA also accepts the same thing. B, or A, or AAB, AB, all of those things, right? So this DFA has two accepting states, but it is deterministic. We know exactly what to do when you're in a state, which other state to go. You can see that when you go from NFA to DFA, we increase the number of states because we combine these states to create new states and see what happens. And by doing so, you can always convert an NFA to DFA. The problem with this approach would be that the states can explode. You will see some examples of that. You can introduce more and more new states, but at some point it's going to get, you will have some control over it. It's not going to be infinite. It's going to stop. So here's another example of an NFA. We can write the transition table for this NFA. Again, understand that if you're in S0 and if you see a 0, you either stay in S0 or you go to S1. Like if you're in S3 here, if you see a 0, you go to S2 or S1 or S0. You can see that. So now by doing this, we are introducing new states. We're going to introduce this state. That's a new state. This is another new state. And here's. So when we completed the transition table for this NFA, we got some new states. These are combination of states, and we're going to call them new names. So let's take a look at what we're going to do. All these new states, S0, S1, we're going to call S4. S1, S3, we're going to call it S5. S naught S2, we're going to call it S6, and S naught S1 S2, we're going to call it S7. Let's see how we're going to fill in the table entries here. I'll show you a few of them, and you can think about the other ones. So here, when you're in S4, which means what are you going to do if you see a 0? So if you see a 0 in S4, that's the same as seeing a 0 in either S0 or S1. So all we have to do is just take the union of these states, which gives you S0, S1, which we call S4. Same thing with the B, or 1, I mean. So what happens in S0 and S1? It's the union of these two, that's S1, S3, which we call S5. So same way you can argue about these states. Let's take a look at S7. So in S7, which is the S0, S1, S2, so what are we going to do if you see a 0? So we look at S0, S1, and S2. The union of these two is S0, S1, which we call S4. And then the union of these three, S0, S1, S2, is S0, S1, S2, S3. S0, S1, S2, S3. And that gives us a new state called S8. So what happens when you're in S8? Let's take a look. In S8, which is the same as if you get a 0, S8 is S0, S1, S2, S3. So we have S0, S1, if you take the union of all these states to figure out what happens when you're in S8, if you get a 0, you take the union of these, that gives you S0, S1, S2, S0, S1, S2. S0, S1, S2 is called S7. Now, if you take the union of these, S0, S1, S2, S3, you get S0, S1, S2, S3. That's called S8. Notice that we didn't get any new states. So this means that we have defined a DFA now. You can replace this by S7. You can replace this by S6. You can replace this by S4. You can replace this by S1, S3, which is S5. So now you have unique states. You don't have a set of states. So from we only had 4 states before. Now we have added 5 more states. So our DFA will have 9 states, and the NFA had only 4 states. So it's the same strings will be recognized by this DFA as the strings recognized by this NFA. So let's go ahead and do another example. We want to build a DFA to recognize this regular expression. This one says either you take A star BD or ACD. So let's try to build an NFA for this string here. So we'll define some states. So these states are defined for A star BD, and 4 becomes an accepting state. And then we will do another one to recognize this. That's going to be ACD. Now we note that this is an NFA because if you're given an A in 0, you can either stay here or you can go to 1. If you look at the transition table for this, you can see that the transition table for the NFA is going to be that if you're given, in the NFA, if you're given a 0 or 1, you can, if you're given a 0 in, if you're given an A in state 0, you can either be in 0 and 1. We call that 5, so we introduce a new state. So let's call that 5 and introduce a new state. And then we'll try to figure out what to do with the 5. So 5 is a union of 0 and 1. So if you take the union of 0 and 1, you get 5. Union of 2 and 2, you get 2. Union of this and 3, you get 3. And that's the 5. Now, if you draw the DFA, which is given by this table, you come up with this transition diagram. Now, it is a DFA because it's uniquely determined. In fact, this A should not be here. Because if you're in 0, you go to 5, right? So you're not going here. So let me just erase that. So that should not be there, right? So now it's a DFA. It's uniquely determined what you do with any given character in any given state. But the problem is, I think you can see if this is a correct DFA or not. Will the BD be accepted by it? BD, so yes, it is accepted. Will the ABD be accepted by it? We can say ABD, it is accepted. Will AABD be accepted by it? AABD, it is accepted. And how about ACD? We go ACD, D? It is accepted. How about AACD? AACD. It is accepted, but we don't like that because we should reject that. The machine is not supposed to accept, for example, this machine is not supposed to accept, it's supposed to accept, if you have a C, it should just be ACD. So that means this machine is not exactly correct. Go back here. So this means that we have to adjust the machine. We can do so by introducing a new state and probably doing some changes to the transitions and still keep a DFA. Probably with the one more state, you might be able to make sure that ACD is rejected. But here's another technique for doing the same thing. We introduce what we call epsilon transitions. So in this case, we think about two machines as two different machines, A star BD or ACD. But given 0, the starting state, I must take a free transition into either one. I can either choose this one or that one. And as you can see, this is still not a DFA, it's an NFA because you have 0, you have two transitions, so that's indeterministic. Okay, so let's see how we can make the table. So the table for this is that if you're given 0, and either you can be in 1 or 2. If you're in state 0, given an epsilon, you can be in 1 or 2. And the rest are not hard to see, that if you are in 1 and you see an A, you stay in 1 and so on. So we have seen many examples of that. The only difference here is that we introduced this epsilon symbol to make this work. So now, because we introduce a new state 1, 2, we have to introduce that here. And then we have to figure out what happens. How do we fill out this table? So 8 is a combination of 1 and 2. So all we have to do is just combine these two things. So if you look at 1 and 2, you get 1 and 5 when you see A. So that gives us a new state called 9. And then 1 and 2 gives you 3 here. So this is okay. And now because we got a new state, now we have to work with that. Now it says new states is 1 and 5. So 1 and 5. So we say 1 and 5, that gives you 1. And 1 and 5, that gives you 3. 1 and 5, that gives you 6. And so here's the table. So here's the new table that we have. And this is a DFA. Now you will notice that this DFA now will not accept AACD. That was our problem with the old DFA. So for example, if you start from 0, you take a free epsilon transition here. But if you have AACD, let's see what happens. If you get an A, you go here. If you get another A, you go here. And if you get a C, now you're kind of stuck because there's no place to go. It's a dead end from 1. From 1, there's no arrow to C. So therefore, you're going to reject that. But one other thing you will notice that is that this now epsilon transition is really unnecessary. And then we can make this the starting state and remove this entire thing. So we can reduce one state and make 8 the starting state. Okay, so this is where you start. And there are a few accepting states here. The 7 and 4 are the accepting states. So you can convince yourself that this machine, in fact, accepts A star B or CD is ACD. So next, we look at some general rules for building NFAs. Let's take a look at that. Because we were doing specific things like using epsilon transitions to get free transitions, and there are general rules for building an NFA. So for example, if you're given a regular expression and you want to build a matching NFA, what we're going to do is we're going to enclose the regular expression in parentheses. We're going to have one state per character, and you will see that in the example. We'll have epsilon transitions, which are red. And we say a black match transition, that means if you see a character, you're forced to go to the next state, and except if any sequence of transitions end in an except state. So let's take a look at how we look at this. So for instance, if you're given the same regular expression A star B A C D, we put the parentheses around that, and for each of these characters, we introduce a state. The leftmost parentheses, the next one, and the A, and the star, and the B, and the O, and A, C, and right parentheses D, and right parentheses, and so on. So we can make the 11 the accepting state. If you want, you can make this the accepting state too. It doesn't matter. Now, the first thing we're going to do is we're going to draw epsilon transition, which are red, from any parentheses to the next one. So because they're like free transitions, we don't read parentheses, so we have to give free transitions. So if we get a free transition here, and a pre-transition to this one, and so on. Okay, so those are the free transitions. So here's another one, and here's another one. So the first thing we do is to add free epsilon transitions from parentheses. This one, this one, this one, this one, and this one. And now we're going to do this one. This is the closure, A star. Now, what A star means is 0 or more A's. So to give 0, we have to say we have to add an epsilon transition. We completely bypass A and then continue. That is 0. But if you take this arrow, that's 1. But we can take more than 1. So we have another arrow going here. So for each closure operation, star, we need to have 3 arrows. One going this way, one going to the next state, and one going back. So you can see that by doing this, we can take as many as we want. Now the or means that either we take this expression or we take that expression. So that's indicated by 2 epsilon transitions. So if we skip this expression completely, we will take a free transition into A and start processing from here. That would give us ACD. Or if you process A star B, then we will skip AC and then go in this direction. So you can see that by taking black transitions and epsilon transition, I can do that. Each character, if there's a character match, it is a black transition. You're forced to go to the next one. That's a deterministic transition that you will have when you see a character. So that's pretty much how it's designed. Again, the rules are, going back to the look at the rules, we will need to do the following. From all the parentheses, we have a free epsilon transition. We have 3 transitions, 3 epsilon transitions from the closure. And then there are 2 epsilon transitions related to the O symbol here. So let's try to simulate the NFA. We want to show that the string AABD will be accepted by this NFA, because we know that if you look at the NFA, if you want A, B, and then D will be accepted. Once again, A, B, D will be accepted. So let's see how we can simulate that. So here's our NFA, and what we mean by simulation is we're trying to predict what are the possible states after reading each character. So start with the empty character. If you read the empty character, you can take all the free transitions. You can go to 1, you can stay there, or you can go to 2. If you go to 2, you can go to 3, or you can go to 4. And that means 1, 2, 3, 4 will be there. But from run, you can also take a free transition into 6. So the set of possible states after reading the empty string is 1, 2, 3, 4, 6. Now we have to determine, after reading A, where can you go starting from these? These are the only things now you can consider. So we look at 1, 2, 3, 4, 6 and see what happens. If you're in 2, you can go to 3, you can come back to A, so 2 and 3 are still there, and also 4, because that's an epsilon transition. So we have 2, 3, 4. Now, because we were in 6, we can also take a match transition, since we read an A, to C. So we add a new state, 7, to this one here. So these are the 4 possible states that you can be in after reading lambda A, empty string and A. Now what happens when you read the next A? Remember, we are looking for AABD, so we are processing 1 character at a time. So we'll start from here and see where we can go. If you see another A, when you're in 2, 3, or 4, you can be in 2, 3, or 4, because you have free epsilon transitions to to go across these states here. But if you read another A, nothing happens. From 7, there's nothing you can do, because 7, you need to get a C to go to the next states. So these are the possible states you will be after reading AA. Now what if you read B? Let's start from here, 2, 3, 4. 2, 3, 4, we know 4 is a possible state where B can be processed, so it'll take you to 5. Okay, you can see that it takes you to 5. Now, can it go to 8 and 9 also? So because we were in 2, 3, 4, so it can go to, if you go to 5, you can also take a free epsilon transition to 8, and you can take a free epsilon transition to 9. So you can be in 8 and 9 as well. So you can be in 5, but if you're in 5, you can go to 8 epsilon transition and 9 and be in 9. So these are the possible states after reading that, 5, 8, and 9. Now the final character comes in, which is D, and we start from 5, 8, and 9 and see what we can do. The only thing that can react to D is the state 9. From state 9, you can go to 10 because you got a D now, and you take the free epsilon transition to 11. 10 should not be here. This should not be here. Let me just erase that here. That's incorrect. It can only be in 11, so in this case, we accept it. All right, so that's how we simulate an NFA. The same way, let's suppose that we want to show that ABAC will not be accepted by the NFA. So let's do the same thing. It's same as before. After reading the empty string, these are the possible states. They don't change. After reading lambda A, after reading A, these are the possibles. They are same as before. Now we are reading a B. So if you're in one of these states, if you read a B, like for example, if you're in 4, you read a B, you go to 5. If you go to 5, you can go to 8 and 9. So you can go to 5, 8, and 9, right? So those are the things that you can be in. So now you're in 5, 8, and 9, you get another A. But if you're in 5, 8, or 9, there's nothing the A can do. This A cannot do anything. So that means you cannot transition anymore, and we don't accept this string, the ABAC string. So that's the end of this demo about NFS.